Mukundan from IIT Delhi on reduction to characteristic E. So Vivek, you are welcome to start your lecture.
Thank you very much. I thank the organizers again for this opportunity. This is the second part, the final part of the reduction to characteristic P. And I did get one feedback saying that it's way too much data for one presentation, but you should understand that this a semester-long course has been condensed down into a two-part series. And I kind of believe that objective of the talk should be to actually give an idea of what reduction to characteristic P is. And if you wish to solve problems using reduction to characteristic P technique, I think you need a viewpoint, and my purpose is to just give you a viewpoint. And the proofs are not very hard; they are very accessible, and I encourage all the graduate students to actually go through the Professor Hofster's webpage and read the proof if you're really interested. But often it happens that you can use those theorems to actually get something really nice out of it. So, okay, so the second part, reduction. Hello? Was there a question? There was somebody talking. Hello?
There is no question.
Okay. So the second part. So what we are planning to do here is give a very brief brush up of what we did on Tuesday and use those techniques to actually solve problems in reduction to characteristic P. And I'm hoping that this talk is a little bit smaller than the one on Tuesday, because I'm also planning to do a little bit on the a general case of Noetherian ring containing a field, if time permits that. Okay, so what we are planning to do here is give the reduction to characteristic P technique for an affine algebra, like what we did on Tuesday. A very fast brush up, and then use that to actually solve problems or application by example using those techniques. Then, if time permits, and I'm sure there will be, give some notes on the reduction for arbitrary Noetherian ring containing a field. Okay, the first is the descent data. What does it mean to descent data in the affine case? So given any finitely generated algebra over a field of characteristic 0, the process is to replace the homomorphism K to R by A to RA, that is replacing the field K, first replacing the field K by a finitely generated Z subalgebra of K, and then further replace R, which is a finitely generated K algebra, by RA, which is a finitely generated A algebra. And such that the descent is kind of natural. So the map from A to RA is induced by restricting this map. So after that, we study the behavior of the fibers, which is got by running the tensoring RA by a field K, which is nothing but A modulo maximal where the maximal runs over a Zariski dense open subset of the spectrum. The idea is that whatever finitely many properties you have in the ring of characteristic 0, you port it over to RK, which happens to be a ring of characteristic P. So if you want to solve problems in characteristic 0, you can try descending everything to a ring of characteristic P and try solving it there. Or if you already know a theorem or a result on the ring of characteristic P, then you can basically try proving the same for the ring of characteristic 0 using the reduction technique. Okay, first descent data given any finitely generated algebra and n contained in M. So whenever X is any object, a module or an algebra, B is an A algebra, then X sub B, where B appears, a ring appears as subscript, is given by X tensor B. Then the descent data for KRMN is nothing but A, RA, MN, NA, which is replacing the K by A, and then subsequently all the algebras and a module by its module or algebra array. So that A is a finitely generated Z subalgebra of K, RA is a finitely generated A subalgebra of R, so that the inclusion RA contained in R induces an isomorphism of RK with R. Moreover, RA is A-free. And the third condition is that if MA and NA are finitely generated A submodule of M and N, such that NA is contained in MA, and you want all these submodules to be A-free, MA, NA, MA mod NA, all to be A-free. Moreover, the inclusion MA contained in M will induce an isomorphism of MK with M. As I explained on Tuesday, the best way to actually get this A subalgebra of K is take a presentation of the ring R over K, the defining ideal of R over K, and collect all the K coefficients appearing in the defining, the minimal generating set of the defining ideal of R, attach it to A, and that forms your V subalgebra. Then once that happens, then you can see that the minimal generating set of R over K actually become available, or it would make sense as a polynomial ring over A. So take the polynomial ring over A and go modulo the same defining equations, and you will get your RA. You can get the property of it being A-free by using the generic freeness condition. And finally, you can descend your modules also down. The way to do that is take a finite presentation of the module M and look at the entries of the presentation matrix of M and collect all the coefficients appearing in the entries of the presentation matrix. Expand your A so that these coefficients also make sense, and then look at the co-kernel of the same matrix over A, and you will get your matrix M. The way to get NA is look at the generating set for N as an R submodule of M, and then collect all the column vectors, and then look at the entries of the coefficient. Expand your A so that those coefficients are also available, and then you define what M mod NA looks like. Then define NA to be the kernel of the surjection between MA and M mod NA. And then again, you generate to make sure that all of these modules are A-free. That's the basic idea of how to construct all these modules. Once you have a descent, then there's a certain type of uniqueness. The idea is to keep increasing your ring A so that all of these modules make sense and all of these descents also become the same. So once you have a descent, you would like to descend not just the submodule properties, you would like to descend the short exact sequences, maps, everything. All of these can be done with the descent data. So the first bunch of properties which can be achieved via descent, if your module is non-zero, then your module, the descent of the module will also be non-zero. MA will also be non-zero. So if you want to preserve the fact that a R linear homomorphism between M and N prime is not injective or not surjective, that can be preserved via descent. And if you have a chain of submodule, the chain can be brought down to the A level, can be descended down to the A level. And if you have a sum of modules in M, submodules in M, then we can increase the ring A so that the sum also makes sense. Intersection can be also be descended down to the A level. The homology of finitely many complexes of modules can also be preserved via descent. The complex itself can be descended. The short exact sequences can be preserved. Homology can be preserved. The homology can be preserved. Then you can make sure that homology being non-zero can also be preserved. Then the split exactness can also be preserved via descent. Further, if you have an idea, then RA mod IA, the descent can be viewed as the descent of the algebra mod I. Again, assuming that you can localize at a non-zero divisor of A. And if RA mod IA is contained in R mod I, since RA mod IA is contained in R mod I, if I is radical prime or primary in R, so is IA in RA. And regular sequences can be preserved via descent. If you have a finite set of minimal prime, then you can arrange your A so that the descent of these individual primes will also be minimal prime of the ring RA. And the next comes the comparison of ideas. The first step is to descend all your properties from R to a RA, which is a finitely generated A algebra, where A is a finitely generated Z algebra. The next step is the comparison of ideas. So if you have a map between A and RA, and P is a prime ideal over A, then we call the algebra from K to RK as the fiber of A to RK over P, where K is nothing but AP mod P. If A is a domain and has a fraction field F, then the F to RF is called as a generic fiber of A to RA. So any property you have of the ring can be pushed over to the generic fiber precisely because the original field capital K is faithfully flat over the fraction field F, therefore it can be pushed over to the generic fiber. The challenge is to actually pass over these properties of the generic fiber to the usual fiber. And if the prime ideal happens to be a maximal ideal, then you get a closed fiber, called a closed fiber. Now comes the most important property, which appears in the comparison of fibers. Because A is a domain, then the property holds for all fibers over prime not containing a certain element, then we say that the property holds for almost all fibers. So equivalently, for all fibers not in over primes in the Zariski dense subset of the spec A. So if you have a Zariski dense subset of spec A, and you take a prime ideal of it, and if the property in R passes over to the fiber over that prime, then you say that the property holds for that fiber. If it happens for all the prime ideals in the Zariski dense set, then you call it to be true for almost all fibers. Why do we study fibers? Well, if you take any maximal ideal of A, then it has a prime number in MA. So A is actually a Z algebra, so it'll have a prime number in MA. So when we look at the fiber, RA will be of characteristic P. So for property holds for R, then we would like it to hold for RK, so that if all the hypotheses go down to the fiber, then you can check it in characteristic P and then say that it also works for characteristic 0. Okay, so what all properties can you descend down to the fibers? Well, if it is geometrically regular, then throw out the fibers for almost all fibers. And if the ring is geometrically reduced, then throw out the fiber for almost all fibers. And if the ring is an absolute domain, then throw out the ring for almost all fibers. The ring is said to be geometrically reduced if the ring which you get after tensoring R with the algebraic closure of K is reduced. Similarly, geometrically reduced if the tensor of R with algebraic closure of K is reduced. And it's an absolute domain if the R tensor with the algebraic closure of R is actually a domain. Okay, so if the ring is Cohen-Macaulay, then throws the fibers for almost all fibers. The ring property of being Goranchian can also be descended down to the fibers for almost all fibers. And the ring being normal also get passed over to the fibers for almost all fibers. If the ring is reduced and S is a normalization, then for almost all fibers, the SK is the normalization of RK. And if J is in the integral closure of I, then the fiber of J will be the integral closure of I for almost all fibers. So this last one is kind of a very interesting one. Even integral closures, Rees algebras, everything just passes over to the fibers for almost all fibers. Okay, so this is what we did for on Tuesday. So the next part is application. How do we solve problems using the reduction to characteristic P? So one of the first problems I'd like to show you is the Honig case result, which says that if you have a d-dimensional Cohen-Macaulay local ring of characteristic P, and if you have a system of parameters and I is generated by one of x t, then the integral closure of I to the n intersects with I to the n minus 1 is the product of I to the n minus 1 and the integral closure of I. This theorem is actually known in more general form. So it's actually known for any Noetherian ring and exponent X is a regular sequence is due to Ito. So you can also check the paper of Ulrich and Zhu Yong Hong for a more general treatment of how this intersection theorem. But nevertheless, this theorem actually comes out pretty easily in characteristic P. Then we will see how to actually get this in characteristic 0 using reduction to characteristic P. So in characteristic P, let's try the proof. So it's clear that the right-hand side is contained inside the left-hand side because I to the n minus 1 I bar is contained in both this one and this one. So it's pretty clear as in the intersection though. So the idea is to take an element here and prove that it's actually inside the right-hand side. So first, a couple of definitions. Vi of x is the supremum over all integers that are x in I power n, and V bar of I is taking the limit of the quotient of Vi of x power n over n. This limit is known to exist, and it is a rational number, and the okay, so that's a rational number, and we can also show that V bar of x is bigger than or equal to k if and only if x is in the ik bar. It's a very nice, very useful result, to check something is in the integral closure. So take an element on the right-hand side. So since it is in I power n minus 1, you can write it as a combination of r alpha, x to the alpha, where x to the alpha is at 1 power alpha 1, blah, 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 x n power alpha n, and alpha is just alpha 1 upon alpha n, and the summation runs over all alpha, so that if you sum up the indices, superscript, you're going to get n minus 1. So that's precisely saying that you take an element in I power n minus 1. Now, you also know that is in the integral closure of I power n, and because of this result, you also get that V bar of I power n is bigger than or equal to n. So that this limit is Vi of Tm modulo m is bigger than or equal to n. Now, this limit also works over by replacing m by p power n. You can use the prime power instead of the integer m, where km is nothing but Vi of tp power. Okay, so now we know that the t power p power m is actually inside I to the km. Therefore, not precisely because of this, what this definition is trying to tell. So if you look at the decomposition of t power p power m, it is just taking all the coefficient and raising it to the power p power m, and taking all these monomials and raising it to the power p power m. So once you have this, you choose an n so that km is actually bigger than p power m times n minus 1. That can also be achieved because of this inequality. Now, you can see that the I to the km is actually generated by monomials in x1 up to xn of power km. But if you look at alpha p power m, it has degree exactly p power m times n minus 1. So there are some coefficients which are left out when you write this guy as a linear combination of the generators of km. So now, if you write this guy as a combination of the generators of I power k power m, and then subtract it out and form an equation equal to 0, and use the fact that x1 up to xd forms a regular sequence, all relations and the monomials of x1 up to xd are basically the causal relation. So R alpha power p power m, the coefficient actually lies in x1 power p power m, blah, 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 xt power p power m, and x1 up to xd power km minus pm times n minus 1. And hence, the Vi element is bigger than the minimum of p power m and km minus p power m times n minus 1. So if I look at the Vi bar, that is just taking this guy, dividing it by m, and then taking the limit, you will see that it's actually equal to 1. That's like saying that the Vi bar of R alpha is bigger than or equal to 1. So R alpha is actually in the integral closure for every alpha. So if you look at the element we took an element P, which is summation of R alpha x to the alpha on the left-hand side. And obviously, x to the alpha is in I power n minus 1. And we basically show that R alpha here is actually inside I bar. Therefore, T is actually in I power n minus 1 times I bar. So we get this result in characteristic P. Now, this term is also true in the for any Cohen-Macaulay local ring containing a field. So if you have a regular sequence and generated by I, then the intersection theorem is actually true in the for any Cohen-Macaulay local ring of characteristic 0. The proof of this in a general case is more long-winded, but I'll just give you a proof of what happens in the affine case, because we basically just finished the affine case. So you will be able to see what happened in the reduction to characteristic. Suppose the proof is wrong. Suppose proof by contradiction. Suppose that the left-hand side is not contained in the right-hand side in a ring of characteristic 0. That means you can choose an element in the left-hand side, but it is not on the right-hand side. Okay, so replace K, start your descent. First step, find what your descent is. Replace K by a finitely generated Z algebra, so that the whole thing, the property actually descend down to the RA level. That is, you can find a UA, so that UA is in I n bar intersect with I to the n minus 1A, but it is not in I to the n minus 1 I bar in A after you descend to the A level. But now, when you go for almost all fibers, Rk can be chosen to be a d-dimensional Macaulay local ring of prime characteristic. Further, you can descend down the regular sequence also. If your F1 up like G is a regular sequence in R for almost all fibers, F1k up like K is also a regular sequence for almost all fibers, of course. But in this setting, you can do something more further. You can make sure that the certain modules are non-zero also. So you can actually descend down the element UK, that UK is in the left-hand side, but not the right-hand side. And this is a contradiction to a theorem in characteristic P, because Rk is a ring of characteristic P, then these two objects should be equal. So that cannot be true. Therefore, this theorem is actually true even in characteristic 0. As I mentioned, that we did only the proof in the affine case, therefore it's much logical to do the proof in the affine case, but this theorem is actually true. Kunicki actually proved it for any Macaulay local ring containing a field, but this intersection theorem is actually true for any Noetherian local ring. Proof by Ito, it's a more general situation. But that proof is a little bit more complicated, because you have to look at the graded piece of the local cohomology of the extended Riesz algebra and check whether that and all. So it can be done using reduction to characteristic P also. The second application I want to show you is the symbolic power of ideals. So for that, you need the notion of type closure in equicharacteristic 0. Again, something which we did on Tuesday. Of course, R is a finitely generated algebra over a field K of characteristic 0. And if n is contained in M, the finitely generated R module, we say that U is in the type closure of N if you can find the descent data such that UA is in the type closure of NA, again in the descent. And the way to check UA is in the type closure of the descent of N, to actually check it for almost all fibers. Remember that if you go to the fibers, then become characteristic P, then you can use the usual type closure definition. But they actually show that you can find just one CA such that CAU to the Q is contained in NK Frobenius Q, NK for all Q bigger than equal to N. Again, for almost all fibers. And they also show that the descent is actually independent. You don't really have to worry about the descent. You can work with any descent you like. And we also, it's also true that most of the type closure properties which you have for rings and ideals is also true in the characteristic 0. Okay, so another definition you require is the Jacobian ideal. So this was finitely generated A algebra, torsion free over A. And A equidimensional over D and geometrically reduced such that R has a nice presentation like this. Then the Jacobian of R over A is the ideal generated by the images of the n minus D side minus of the Jacobian matrix. So Jacobian matrix is the matrix of partial derivatives of the defining ideal of R with respect to the variables that one apply. It can be further shown that if you have a map between A and B is reduced and flat over A, that RB B tends to R, then the Jacobian ideal of RB over B is also defined, which equals the extension of R over B to the ring R. So R is basically RA, but yeah. If you have two maps, and A from A to R and a map from R to F, and the Jacobian of R over A is defined, Jacobian of S over R is defined, Then the Jacobian of S over A can also be defined, and further, the Jacobian of S over A contain the Jacobian of S over R times the Jacobian of R over A. Okay, so next is the theorem. So this is the theorem in characteristic P. If you have a geometrically reduced equidimensional K algebra, finitely generated field of characteristic P, and I be an ideal such that for every prime ideal Q, IRQ either contains a non-zero divisor or H is the largest analytic spread of IRP, where P runs through all the associated primes of I. And if you have J is your Jacobian ideal, then for every K, the product of J to the n times the Hn plus Kn symbolic power of I is contained inside the tight closure of the nth power of the K plus first symbolic power of I. Furthermore, if you raise the J power n to I to the n, then you can forget about the tight closure. So this can be done using the tight closure technique. More than giving the proof, I'm more interested in giving the idea behind the reduction to characteristic, because giving a whole lot of proof of this will take a lot more time. The same proof is actually true even in a ring of characteristic 0. So if you assume that the ring of characteristic P is true, how to actually prove the ring of characteristic 0? The idea is pretty much the same. Suppose you take an element that this is in the left-hand side but not the right-hand side, then the replace K by a finitely generated Z algebra A, so that there exists a counterexample in RA over A, so that RA is contained in A and R is morphic to K times RA, the first step of the descent. That means we can descend I to IA, such that the UA is in this one but not the other one. Then since A is excellent domain, localized at one element, so that to make A is a regular domain. In fact, localizing at one element, you can make sure that A is actually smooth over Z. And since you have two maps between from Z to A and then A to RA, the Jacobian of the product is contained inside the Jacobian of RA over Z. Since A is smooth over Z, the Jacobian of A over Z is basically the same ring A. So the Jacobian of RA over A is contained inside the Jacobian of RA over Z. So instead of working with A, we can just work with Z instead. So for almost all fibers over the close point Z, we have that UK is contained in here but not here. There's a contradiction to your theorem in characteristic P. We can make a quick work of the theorem. Again, this is the affine case, not the general case. Okay, the third example is a reasoned result of ours, which shows that if we have a homogeneous ideal in a standard graded ring over a field of characteristic P with a homogeneous macronide lemma, or an ideal in a regular local ring of characteristic P macronide lemma, if the R mod I is Lorentzian, we show that the Cn symbolic power is inside m times I to the n. So the same result is also true for the characteristic 0 case. The way to go about that is first construct your ring A. So first make sure that you have a contradiction. Suppose U is in the Cn symbolic power, but not in mi power n. Do the first step of the descent, that is replacing the K by a finitely generated A algebra, and then send down your ideals, rings, and the primary decompositions and the prime ideals containing I. Then we descend I to IA as well as the ideals and the prime radicals and prime decomposition. We make sure that this element after descent is in I to the Cn but not in the m I to the n. Then since A is excellent domain, the same technique, you want to make sure that you want to make work over Z instead of A. Localize at one element so that A is a regular domain. A non-zero element is localize at non-zero element to make sure that A is smooth. Then for almost all fibers, you can also preserve the property that the R mod I is Lorentzian after you go to the fiber level. But for almost all properties, if R mod I is Lorentzian, then this cannot hold true because we have already proved it in characteristic. Proof of the characteristic P case is also takes a couple of more steps. I thought I'll restrict myself to reduction to characteristic P case. Okay, since we have more time, what we can do is go over to the reduction to characteristic P for arbitrary ring. So there are three steps basically if you want to apply the reduction to characteristic P technique for any Noetherian ring containing a field. First step is localized and complete. Second step is descending from a complete case to the affine case. This is by far the most hardest case to do. And the third step is to use our usual reduction to characteristic P in the affine case. Reduction to characteristic P in the affine case can easily be achieved. Can be achieved, not easily, but can be achieved. That's what we've been doing for the past 1.5 hours on Tuesday and today. But the most important part is to actually descend from the complete case to the affine case. And I kind of removed the proof for the two examples I just presented, basically because I wanted to give an idea of what the part two actually means. Okay, so the main tool you have to use for this is the Artin-Rothaus theorem. It's a pretty deep theorem. It says that K is a field and T is a power series ring over F1 up Xn. S is a finitely generated K subalgebra of R of T. There exists a factorization from S to R to T so that R is obtained by algebraic elements X1 up Xn, Y1 up Yt by localizing K X1 up Xn, Y1 up Yt at a maximal ideal, X1 up Xn and Y1 up Yt, then taking it Henselization. The Henselization is actually a very important concept because it lies in between the local ring R and its completion. And they usually define through the direct limit of point-to-detail rings, and it's a Noetherian ring, and it's in fact is faithfully flat over R. So it can be viewed as an algebraic completion. For example, if you have a polynomial ring and localized at the maximal ideal, the Henselization would be the collection of all power series to satisfy an algebraic equation. And because it's faithfully flat, if the ring is regular, the Henselization will also be regular. And therefore, what the theorem is trying to do is, if you have the map between S and T, it factors through a nice regular ring where F1 up Xn actually as part of a system of parameters of the Henselization of R. So, of course, it's in no way true that R actually sits inside T. That's not true at all. But S definitely sits inside R. And this is one of the main tools which is often used to reduce the problem from a complete local ring to a finitely generated K algebra. This R is actually a finitely generated K algebra. So whatever problems you have for a complete local ring, you can push, if you have finitely many equations, finitely many data in the complete local ring, you can push it over to the finitely generated K algebra R and go through this method. The main tool is that whatever property you have for T, you can make your S large enough so that they make sense. So the property in T makes sense in R, in a sense that it may not be true in S, but you can make sure that the equations and the maths actually make sense over it. So even though the property doesn't descend down to S, this theorem basically says that it actually descends down to R. Okay, so one quick theorem on for the Noetherian ring containing a field. This due to again when a K is suppose, and again I should also mention that the K need not always be a field. It can even be an excellent DVR. The theorem is still true. Okay, so the theorem on characteristic 0. If you have a field of characteristic 0 and you're given a complete local ring, that is also a K algebra, assume that S is equidimensional and unmixed, and suppose your R0 is a subring that is a finitely generated K algebra. And we are also assuming that we are given a finite set of finite sequences in R0 such that each of them can be extended to a system of parameters of R. Okay. Then there exists a finitely generated K algebra R. This is the important part. So you have a finitely generated K algebra R, such that this inclusion factors via R, and R has all the nice properties which S has. R is bi-equidimensional. The image of these sequences also form a part of a system of parameters in R. And if the difference of the dimension and the depth of R equals the difference of the dimension and the depth of S. So in effect, if you know S is Quanticoly, then R is also Quanticoly. And if S is reduced or a domain, then 4 is R. I wanted to give the proof of 1 and 2, basically to give an idea of the how to get the ring R. I mean, it's kind of really interesting and extremely hard thing to even think about. You're given a complete local ring which has a certain property. You are actually trying to build your finitely generated K algebra such that all these properties get transferred over to R. So to the proof. First, assume K is equal to L, and then fix a system of parameters x1 of Xn for S, and view as an S as a finite module over the power series string x1 of Xn. So this is a consequence of the coin structure theorem. So basically, T sits inside S, and S is a finite module over the power series string. So Xn, each of these partial system parameters you get to a full system of parameters. And then make sure that, and make your R naught bigger so that all these elements make sense in R naught. Okay? Then because x1 of Xn is a system of parameters and its ZITs are also a system of parameters, some power of the ZTIs can be written as a combination of Xi's, and some power of the Xj's can also be written as a combination of the ZTIs. So make your R big so that these coefficients actually belong to R naught. I mean, make your R naught bigger so that these coefficients actually belong to R naught. The consequence is that these equations hold true in R naught. Therefore, in R naught, the radical of x1 of Xn and the ZIT are basically the same thing, are preserved. So once you expand this, it's actually enough to work with just x1 of Xn rather than working with all the ZIs and ZIs. Just concentrate on x1 of Xn. Okay, so first write S as a finite module over T, where theta1 is 1 and theta2 over theta E are the extra minimal set of generators you need to write S as a finite module over T. Then since S is equidimensional and is unmixed, it's torsion free. So you can take a copy of S inside a free module over T. Now choose a minimal free resolution of S over T, which you can write it like this, where the co-kernel of alpha 2 is basically your S. And you have an extra map alpha 1, which is a composition of T to the D with S and S inside T power. So T to the D to S is the co-kernel map of alpha 2, and S sits inside T power eta also. Okay, so these entries in alpha are actually in T. Therefore, they can be written in terms of the x's. Therefore, you have to make sure that they are also inside R naught. But instead of doing that, after you make sure that R naught has all these entries, you can use the Artin-Rothaus theorem, which we just showed, so that every finitely generated L algebra with map to T also map to an L algebra D that is a regular domain in which x1 of Xn is a regular sequence. So your idea is to actually replace the T by a nice regular domain D, where x1 of Xn is a regular sequence. We call such a D as permissible. From here on out, we are going to keep extending our ring D so that finitely many data points, like the entries of the matrices or the composition of maps or the homology being non-zero, all of them happen to hold true, have liftings over D. Okay? And all that can be done by the Artin-Rothaus theorem. Suppose that it so happens that some of alpha 1 has a lifting, but alpha 2 doesn't have a lifting. Then you find another permissible algebra D prime that alpha 2 also has a lifting. So keep doing that so that all of these alpha i's have lifting to D. So since all of these entries are linear combination of the xi, we may choose a sufficiently large permissible algebra D. So that permissible algebra means that it comes via the Artin-Rother theorem. So that the entries of alpha i's have lifting to D, and the lifted entries are inside X1 up X D. Remember that X1 up X D forms a regular sequence inside D, again as a consequence of the Artin-Rother. You can also make sure that the I element that are linear combination of the Ri size minus of alpha I, so that I element can be extended to a sequence of length n in D. Now, one thing you should note here is that this is actually a free resolution. So by the Bushbaum-Eisenberg theorem, you can see that these maps, the rank level maps of rank level minors of these maps have depth at least I. That's the Bushbaum-Eisenberg acyclicity theorem. So what that one is saying is that if I look at the rank level, Ri level minors of alpha I, you can find some linear combination of the minors, or not linear combination, combination of the minors of Ri level minors of alpha I, that forms a sequence of length I. Make sure that that can be extended to a full sequence zeta I of length n in D, which has the same radical as X1 of X. And this is the same technique we did for the Zi's at the beginning. Once you have all this data, what happens is that you can think about these alpha 1, alpha 2, all these alpha i's as matrices over D, because they have lifting to D, they are works over D also. Now, remember that we also made sure that the rank level minus having depth I also have a lifting to D. So all these rank level minors have depth at least I, therefore by the Bushbaum-Eisenberg cyclicity theorem again, this forms an acyclic complex. Once you have the acyclic complex, remember that you wrote the cokernel of alpha 2 as S. But now over D, you write the cokernel of alpha 2 as a new symbol, RD prime. So RD prime is a finitely generated D prime module. That part is clear, but I'm using D prime because you want to make sure that D prime is big enough so that all these properties hold. So after localizing at a maximal ideal, which is a contraction of the maximal ideal from D, this becomes a free resolution for RD prime M prime. Therefore, the dimension of RD prime at M prime minus the depth is the same as the PDIM, the outline of the formula, which is the same as the PDIM of F, because these are basically the same exact sequence. That the dimension PDIM, again, by using the outline of the theorem, will give me dimension S minus dimension of D. So the part 1 and 2 in our theorem could have been done easily, or we would have gotten the statement 1 and 2, that is the Z's becoming a system of parameters, and the fact that you can make R to be a Cohen-Macaulay local ring if S, provided you have a nice candidate for R, and also make sure that R is actually a ring. Here, you define your R D prime to be cokernel of alpha 2, so still a module. So this could have been a nice candidate for your ring R. So this is the first step in constructing your ring R, through which the map between R0 and S factors through. The only issue is how do I define multiplication for module? But you have a way out of that one too. So if you look at RD prime, which is the cokernel of alpha 2, it also has the same generator, theta 1, theta 2 up to theta b. So you can make sure that for all large permissible D prime, RD prime is actually a finite module over D prime using the same generator, theta j. Now you can multiply theta j times theta k in S for sure. Because theta j and theta k are honest elements in S, which is a ring, so you can multiply them. If you multiply them, you get a ring back in S, which is a finite module over T. So you can write it as a combination of theta v with some coefficients which appear in T. So now choose another permissible. You enlarge your D prime so that these coefficients make sense in D prime. They have a lifting to D prime, and then you have your multiplication. Or if you want to get the commutative ring structure, make sure that you look at theta j, theta k, and theta k, theta j. That hold true in T, therefore you can still make your D prime bigger, permissible D prime bigger, so that the same equation also holds in R D prime. You can get the commutative ring structure, the associativity, and all that kind of stuff. You get an honest ring that the product of two theta j and theta k is the sum of with respect to theta j. Now, R D prime is also a module finite over a domain D prime, where S is isomorphic to T tensor with R D prime. And once you have that, one another important property is that R D prime actually maps to S. So R0 sits inside D prime, and D prime sits inside R D prime, and that's a map to S. In consequence, we have for a finite set of elements in S, a finite set of polynomial relations over L, then if D prime is sufficiently large, all of these can be lifted to R D prime themselves. So this is your first choice of your ring R. So each of these elements, theta 2 to theta b, have a power which is inside the ideal generated by x1 up to xn in R D prime. And R naught to S, actually, R naught sits inside S, is an injector map, actually can be factored through R D prime. Then the macro ideal of R D prime is M intersect with R D prime, which is N. Then we can take R to be R D prime localized at this macro ideal. I mean, I forgot the localization. It should be localized at this macro ideal length, so that all these conditions are satisfied. And R can also be embedded into D prime M the same way S can be embedded inside T eta, T to the eta, free module to the eta. Inject one of Xn forms a regular sequence in D prime due to the Artin-Dot theorem. X1 of Xn forms strong set of parameters in D, and the Cohen-Macaulay now follows because of 11, basically. So it follows because of this one. Cohen-Macaulay follows because of this. You make sure that in R D prime, the ring, these two hold true. Therefore, if one of them is 0, the other will also be 0. So Cohen-Macaulay. So essentially, you replace or you descended all the properties you have for the complete local ring to a finitely generated K algebra R. And once you come to the finitely generated K algebra, then you can use the descent and comparison of fibers to further reduce it to characteristic P and solve your problem. So it's not just the fact that you can descend the system of parameters, Cohen-Macaulayness or reduceness or domain. You can still descend a lot more property. As again, a theorem of Hochschild and Hoenicke, they show that if K is a field of characteristic 0, SMNL is a complete local ring. A finitely generated K algebra R naught is large enough such that it contains all the entries needed for the presentation of the module and the map. So you are considering finitely generated S module with specific presentation, and finitely many maps of these modules, S module, finitely many specific equalities among the composition of these maps, and finitely many short exact sequences, and finitely many finite complex of specified homology, finitely many submodules of modules in one, and finitely many intersection of modules, finitely many sums of modules, whatever. Or if you're given finitely many ideal geners with specific generators and finite subset of finitely many associated prime of a certain height. If you're given any of the finite set of data, you make your ring R0 sits inside R large enough so that these entries and these rings make sense. The theorem says that you can actually construct a finitely generated K algebra R such that the map between R0 to S factors via the R such that the specific presentation of the maps of modules over R and the specific exact sequence of modules descended to R also are the one from R0. And all the relations in R0 also hold in R0, in R, I mean, and including the homology of the complex and finite, some finite intersection, everything goes over to R. And unmixed ideals are also preserved in R. And if the ring R is regular, if the original complete local ring S. So all of these properties which you had in a complete local ring can be pushed further to a finitely generated K algebra. That is all I have for you today. Thank you very much. Hello?
Yes, are there any questions? Okay. So I have a general question, Vivek.
Yeah, sure.
I mean, we have seen that many theorems which were very deep and proved by analytic methods.
Right, the aunt and daughter theorem, yes.
Right. So they found very simple proofs in characteristic P. And then we have this method to prove them back for rings containing a field.
Yeah.
So the complication lies only in setting up this data, but
exactly, perfectly. That's the
otherwise,
right.
Otherwise, the process is simple.
Right. You have to make sure that all the hypotheses you have to prove your result actually passes all the way from the completion to locality, then to the finitely generated K algebra, all the way to the fibers. If you can make sure that the hypothesis follows, and then you can prove and from characteristic P to characteristic 0.
Mm-hmm. Yeah. So Sarang has a question. Where was permutability of the regular sequence used on page 29?
Well, permutability is not really used. That was used in the net proof for the domain and stuff, but you just need regular sequence. Yeah. I mean, there was one. Yeah. Yeah, so it's actually used here, but I'm not giving a proof of that. But it appears as a part of the proof. You don't need it at the moment. Yeah.
Okay. Okay. Yeah. Right. So, are there any questions? Okay. So, if there are none, we shall meet next week, and we have talks by Matteo Barbaro on F-splitting of polynomial ring, and Mandira Mondal on density functions of for the coefficients of Hilbert-Kunz function of polytopic monoidal algebra. So we will all gather once again next week. Thank you very much. And let us thank Vivek for his nice talks. Yeah.
Thank you. Thank you, sir.
Thank you.